Turbulent intensity inside a flow is linked really closely to both its shear stress and its shear velocity. What do these mean? So a stress is a force per unit area, and a shear stress means that that force per unit area is occurring in a direction that is, parallel to that particular surface. So, for example, if I have a surface that's like this horizontal line, if I have a stress marked with these blue arrows, that's just going towards the line on both sides. Make this one a little straighter. This would be a normal stress. But because it's going normal or perpendicular to that surface. In green, I'll create a shear stress, and a shear stress is a stress that's going to go parallel to that surface, and so we're going to have this, ooh boy, garish green. And as you can see, that shear stress is like, rubbing your hands together, whereas the normal stress is like pressing your hands into each other. And you can kind of feel if you push your hands closely and start to rub them back and forth like I am, you might be able to pick that up on the microphone right now. You feel some friction, and that friction is related to the resistance of your hands being able to slip against one another. Inside a fluid flow, you can imagine that shearing force, that kind of pushing something kind of along to the edge, just like imagine if you're standing next to a wheel and you start hitting it on the surface in a shearing way where you can actually get that wheel to go. And so you imagine back in the day, kids running around the street with a tire, or if you've ever had to just move some car tires, you push them on the surface, on that top surface along, and you can get them rolling. And that is the shear stress. And so within the flow, the same thing happens. A shear stress acts on the surface, and as a result of a shear stress, I'll make it the same green, acting on the surface of that particular eddy, just gave it away, what happens is that there is going to be some motion that is in the direction of that stress that's being imparted. So this is the link between shear stresses and eddies, and we have a term that we call the shear velocity, which is a velocity that's associated with that stress, and the shear velocity ends up giving us information about the intensity of that particular turbulence. So we can think also about the different length scales of turbulence and where it's important, right? Because does the shear stress create really large eddies, right? Are we talking about, eddies that are gigantic, like this? Or are we talking about little tiny whirls of eddies that are like this? And it turns out that eddies exist at multiple scales. And there are a couple different scales that are really limiting. One of them is the smallest length scale called the Kolmogorov length scale. And the largest eddies will exist at a length scale that's related to the total depth of the flow. So if we're thinking about eddies in the vertical. So if this is h equals flow depth, then that's the depth at which these largest eddies occur. And these smallest eddies will exist at a length scale that's given by the Kolmogorov length, below which viscosity takes over and dampens the ability of any eddies to form. So there's a nice little poem written by Louis Fry Richardson, a fairly famous scientist back in the early part of the 20th century, who wrote, "Big whirls have little whirls that feed on their velocity. Little whirls have lesser whirls, and so on to viscosity." And that is exactly how this cascade of turbulence works, from these really large spinning whirls that start at the full flow depth and all the way down until we get to the Kolmogorov length. So the other convenient thing about starting to discuss shear stresses right now is that same shear that we're talking about that creates eddies in the flow and might create different flow velocities also acts on the layer between the bed of the river, or the layer at the bed of the river, so between the flow and the sediment. And so that shear stress ends up moving the sediment grains and leading to erosion and particle motion, and that's where we're going to take this whole discussion of fluid mechanics all the way back to geomorphology in the shape of river channels. So a couple things first as we get going. So above here, we know that this concept of uniform flow. In the solutions below, we're going to forget about this for a little bit because I want to show you how pressure gradients end up canceling out if the flow depth stays constant. And so we're actually going to go and kind of back up out of this assumption and then revisit this assumption, showing how it comes about. These solutions will, however, all include this assumption of steady flow. And of course, we know that there are lots of accelerations related to eddies and turbulence. That's what we're talking about, right? We have these little bits of variability that we can see where if we have, for example, a flow velocity versus time, there's going to be some u bar where the flow is staying steady, and that flow velocity is going to bounce up and down over time around that mean, but it's going to generally stay somewhere relatively close to it. And so we are going to be averaging out over all of these turbulent fluctuations and saying that this is quasi-steady, in that on average it's steady, in order to make that assumption. Scrolling down here, so here is a nice little free body diagram that I gratuitously lifted from Kellen Whipple's course notes from back when he was at MIT. And so Kellen Whipple is a geomorphologist at Arizona State. And so he has this diagram that shows two different depths of water columns. So this is all water. And so we have this depth at location H, and this depth at location X plus, this depth H at this location X, and this depth H at location X plus delta X. And at this location X plus delta X, we can see that the depth is actually bigger, right? So we have this situation where H of X plus delta X is not equal to H of X. And that leads to a pressure gradient. And so the pressure at this point here, X, is given by the density of water times the acceleration due to gravity times H of X, which is the depth of the flow there. Likewise, the pressure here is given by the density of water times acceleration due to gravity times the flow depth at this location X plus delta X. And what we can see then is that if we assume, and this is what this little number 2 is, so assuming constant density, that we can approximate the pressure gradient that's driving flow to be related to gradients in flow depth. And in other words, what we're saying is that by the definition of a derivative, and just as a little reminder, you can think about this dp dx as, what is the pressure here? What is the pressure here? And remembering that for the definition of a derivative, we take the term at the farther downstream point if x is positive in this direction. So x is increasing this way. And, pardon me, and then subtract it from it, the value over here at the lower x value, and divide that distance delta x between them. And we can see that we have x and we have x plus delta x. And if we expand that pressure, so we can say this is just going to be p of x. I'm going to draw my p's like that to make sure that they don't look like these Greek letter rows for density. So p of x, not enough space, p of x plus delta x. So we have these two terms, they go into here, and they become part of this dp dx equation. If density were different between these two locations, we might have to think about that other term. For example, if there's, we're dealing with water and oil, or fresh water and salt water, or a, for example, if we had to consider about something like a tanker truck full of, some kind of like sugary, sticky, dense syrup, interacting with a river after a major tragic car accident. that sort of thing, we'd have to think about the density, but right now we're just thinking about water, so we can ignore the density terms. Or by ignore, I mean we can take this density term out of the derivative, as well as gravity, because gravity is a constant. And we pull these over here, and so we can say that the pressure gradient is related to the gradient in flow depth. And flow moves from zones of high pressure to low pressure. And so in this case, what we would actually see then is that there is a portion of the stress related to pressure, and that's actually pushing things back upstream. And so I'm going to say tau sub b, so this is a basal shear stress, so shear stress acting on the bed of pressure, because this is higher than this, is pushing that flow back upstream. Of course, there's a second force involved, because we're on a slope and we're on the Earth's surface, and the Earth has non-zero gravity. And this is related to what we call the body stress. So the weight of a block of water is just equal to the same thing that we were talking about, this rho gh, where once again we have this rho, which is water density, this g, which is acceleration due to gravity, and this h, which is the depth of the flow. And that is the weight that's just pushing straight down, right? So this is the weight. So that's the vector. But that weight is combining both the normal stress and the shear stress on the bed. So if I sketch an example like downslope, river channel. So if I have a slope like that, and then I have some water on the surface of it, that's supposed to be approximately parallel to that. There we go, getting a little bit better with this pad. So what we can see if we have those two lines is that there will be two separate components to this. If we have a overall weight of the water that's going straight down, there's going to be one component over here. See how many colors I can use. So there's going to be one component over here, which is the normal stress component, and then there's going to be another component like this, which is the shear stress component. So I'm going to call this one sigma sub b, which is the normal stress. And we're going to ignore that term, because that's just the ambient pressure being placed on those rocks. And that's isotropic, so it's equal in all directions. And then there's another term that we can think about, that is the shear stress that's acting on these. And so we'll call this tau b, so the bed shear. So basal shear stress. And of course, there's shear stress that occurs on every single one of these little tiny imaginary layers that you can think of inside the flow. And so you can imagine that this flow might consist of, like 1, 2, 3, 4, all these different layers, and there might be different velocities inside these different layers that's creating stress between them. But, But regardless, what we're thinking about is the stress that's on the bed right here. So big arrow right there to indicate that we're thinking about the shear stress here. And from trigonometry, if we create an angle and define this angle as alpha, right there, what we can see is that if we run a decomposition of this vector in these two different directions, that this basal shear stress from the body forces should be rho gh times sine of alpha. And I'm going to note here that this tau b, just so we don't get confused, is tau b sub body for body forces. All right, so pardon me, for most river channels, alpha is small. And so therefore we can use a small angle formula to approximate that tau b of the body forces is rho gh times slope. So this little figure ended up on the next page because I ran out of room there, so we're just going to remind ourselves of what the small angle formula means. And so if we think about an angle like this, once again I'm going to have like this, and this is going to be the horizontal plane, and so we'll have this angle alpha. And we know that, so slope, which color to pick now? I'll just keep it green. So slope is equal to tan alpha, right? And what we're trying to do is figure out how sine alpha can eventually go to slope. So tan alpha is also equal to sine alpha over cos alpha. And if alpha is really tiny, then the length of this, so I'm going to call this, this is going to be the adjacent angle, right? So this is going to be this is the hypotenuse, L hyp. And this is going to be the adjacent side of a right triangle that's formed right there. And then this right over here is L adjacent. And we can see just geometrically here that as alpha approaches 0, that L adjacent approaches L hyp. Right, so the length of the adjacent side of that triangle is approaching the length of the hypotenuse. And for small values of alpha, the length is approximately the same. So for small alpha, so length adjacent is approximately the same as length hypotenuse. And that becomes important because cos alpha is equal to, by definition, the length of the adjacent over length of the hypotenuse. And if we take this piece of knowledge in here, we can say that that's approximately 1. And therefore, for this situation then, we have sine alpha is approximately tan alpha, because tan alpha is equal to sine alpha over cos alpha, and cos alpha has just gone away to become approximately 1, and so therefore disappeared from this equation. So zooming back up, I'm going to look at this equation. I'm going to pick my most wild color. Let's pick this hot purple. I'm going to box in this equation and put an arrow here because this is super important. This is what we call the depth-slope product. And so this is the solution for the body force impact, or the body force driven shear stress in a river. And this is, in fact, the equation that we're going to be using almost all the time in the future of this course for computing shear stresses inside river systems. And I think that actually there isn't really a whole lot more to say about that, except for the fact that you might wonder why I went through talking about the pressure force and how we're going to get rid of it. So let's scroll down. Let's combine these pressure and body stresses, and I'm going to take a slightly less intense color. Let's go back to the screen. And so the total basal shear stress is going to be the body stresses plus these pressure stresses. Let's move back up here, and so what we can see is that we have this back pressure occurring because this depth is greater than this depth. But then we still do have, going down here, tau b sub body. And I'm going to make this be a big arrow because it's going to be overwhelming this back pressure from this. And we can tell it's overwhelming this back pressure because the overall slope of the water surface is still going left to right. The pressure forces balance out the body forces, once the surface is horizontal, right? That creates a lake. And so if we say that that we're dealing with body forces plus pressure forces, we can combine these two together. And we talked about this earlier when we discussed the backwater equations, and these are important when flow is accelerating towards a lip like a waterfall or decelerating as it's entering a body of standing water. So when flow depth is uniform, the pressure forces disappear. So it goes to 0 when, oh goodness, I can't write today. Let's just make this easy on myself. If, fewer letters. So it goes to 0 if dh over dx equals 0 and density is constant. And you know what? When you're looking at water flowing down a river, it's very, very common that there isn't a whole lot of change in the overall kind of average flow depth. You know, if you kind of take an average over one cross section of a river, take an average over another section downstream, another section further downstream, they're not changing all that much. So this is actually a really good approximation that we can have this basal shear stress be approximately the same as this body force. And so that force then disappears and gives us, once again, the depth slope product. And I used the approximation symbol before, but you know, slope is so gosh darn close to sine of alpha, and it's definitely close to within our ability to generally estimate depth or think about possible changes in flow depth, that this is just we can essentially take this as an equal sign. So here we are. This is our equation that we're going to use, and this is going to be shear stress on the bed. And then let's go back to thinking about how that shear stress might relate to a velocity. So shear stresses actually scale as flow velocity squared. And so we can think about a particular velocity. We're just going to call this the shear velocity. And this isn't a real velocity that occurs within the flow. This is a made up velocity in order to be able to compare the velocity that's essentially driving the turbulence. So it's driving the shear between these different layers on the flow. And by definition, the basal shear stress is equal to the density times the shear velocity squared. And let's use steady uniform flow, which means that we can use this equation right here and do the math to figure out what actually sets this basal stress. And I have the answer down below there, but let's just make sure that we can all get there together. So we have rho GHS, so this is going to be the tau b term, equals rho u tau squared. And u tau is sometimes also written u star. So it just takes a little bit of algebraic rearranging. We can cancel out these two density terms, and then we have the squared. And we can take the square root of both sides. And you might remember from math class that, if we take the square root of both sides, we have to have a plus or minus, because, this could be negative. This guy could be negative and be squared, and that would take care of that minus sign. But we don't have rivers with negative flow depth, so yeah, it's just going to be positive. That's a physical constraint on this mathematical system. So then what we can say is, therefore, that u tau, this expression of turbulent intensity, is equal to the square root of gravity times the thickness of the flow times the slope. And this is a velocity scale, as I mentioned, that drives turbulence. And therefore is going to be important in turbulent velocity profiles. Flow velocity and velocity profiles. by which I mean the variation of velocity with distance in the vertical in turbulent fluids. And so this shear velocity then is going to appear in our next several equations. Just a little sneak peek down below. So we're going to set up some empirical and semi-empirical laws to understand how turbulence helps to drive flow. And we're going to eventually go into a more formal law called the law of the wall that is derived directly from theory about turbulence. And from there, we're going to exit this fluid mechanics chapter and move back into understanding rivers and their morphologies. But just to give you a quick thought experiment before we end this little lesson, if you think about the shear velocity, that's relating to the shear stress. If you think about the shear stress is going to go up if the flow is steeper or if the flow is deeper. And deep, steep flows move quickly and impart a lot of stress onto the bed and therefore seem to be able to create more turbulence. And those fast flows that are also deep mean that there's going to be a higher Reynolds number, right? So that's also consistent with more turbulence. And so you might then think that those deep, steep flows, I guess I already gave it away. They're going to move faster. And so that is going to be the relationship between the flow velocity and the shear velocity. And the shear velocity is also going to be able to give us how intense these eddies are moving fluids parcels within the flow. And fluid parcels close to the bed are going to be moving slowly due to the friction against the bed. Those far from the bed will be moving more quickly. And these whirls mixing fluids vertically will mix some of that fast fluid from up top with some of the slower fluid from down below and tend to homogenize the velocity profile. And so that's the other piece that we're going to talk about when we go through the law of the wall, is what is the actual shape of a velocity profile in a turbulent fluid, and how does it relate to this intensity of turbulence?